Howdy and welcome back. So finding the minimum and maximum keyed node within a binary search tree is going to be quite straightforward. The reasoning being is that the nodes are going to be arranged within our binary tree to satisfy the binary search property. So let's say we're looking for the minimum value. Where would that reside in the tree? Well, if we have a root X, like maybe this, let's go with the kind of funky colored one at the top, the minimum value is going to be this node. Why is it that node? This is as far left, as you can go. Remember, if we start at the root, the minimum value or the value less than the root would be found in the left subtree. Okay, so now we move to the left subtree. All values less than this key would be found in the left subtree. All values greater than the key of the, let's go ahead and highlight it, of this node here would be found in the right tree. So here, the key values, keys greater than or equal to that one. Here, the keys would have been less than that node. So sorry, that doodling's a little funny, but hopefully you see where I'm going with this. So if you wanted to find the node with the smallest key value, what are we going to do? Well, you just keep stepping left until you can step left no further. And again, that's because for each node you arrive at, the node whose key value is less than it is always in the left subtree. So if you just keep walking left, 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 you'll eventually arrive at it. So minimum value. I guess I had a diagram here I could have used to illustrate this. This looks actually a bit nicer than the one from the CLRS textbook. But anyhow, let's go ahead and do this. So minimum value. We find the element with the minimum value by following the left pointers as far left as possible. So look here, we now have this binary search tree, or this binary tree that satisfies the binary search property. And what is the smallest key value here? Well, we start at the root, and we know that the node containing the smaller key value than that stored at the root would be to the left of it. So we step to the left. Now we go ahead and we check and we see, is there a node to the left of that with the key value of 8? There is, so we can step to it. So while the node has something to its left, we step there. And then when we can step no more, because that node's left pointer is the null pointer, guess what we've just arrived at? We've arrived at the minimum value. So the algorithm to find the node with the minimum key value is just simply while the current node that we're on, so we start out current node. Well, current node's left is not equal to the null pointer. So in this case, it's not equal to the null pointer. We go ahead and we break that connection and move it here. So current node now points to the node with the key value of 8. Okay. Does current node's left store the null pointer? No. So we can step left. So we break this connection by saying current node's equal to current node's next and move to the node with the key value of 4. Now guess what? Current node's left is the null pointer. So at this point, we don't get into the body of our while statement. Instead, we jump out of it, and guess what the last line of this function is? Return the address of the node we're currently on, which is going to be the node here with the key value of 4, or in other words, the node with the smallest key value found within our tree. Pretty straightforward. Again, this walk is almost like that of a singly linked list, and I keep bringing up singly linked lists because I'm trying to create the connection here that it's we're just kind of moving. In this case, we're always moving in the same direction. It's very linear because we're just stepping left as far as we can go. When we can no longer step left any further, by definition of the binary search tree property, we're at the node with the smallest or minimum key value found within that tree. Now the maximum tree value, what do you think you do here? It's going to be the identical process, but in the opposite direction. Because remember, if we look at our binary search tree property, if X is a node in our BST and Y is a node in the right subtree, then it is guaranteed that the key value of Y is going to be greater than or equal to that of X. So if you move down, say from the root to the node at the top of the right subtree, its right subtree would be guaranteed to have at its root a key value greater than the current node that you're on. So here, for the maximum value, we start at the root or whatever node address is passed into this function. So here's current node. And then we simply say, while current node's right is not equal to the null pointer, move right. So we break that initial connection and current node points to the node with a key value of 22. Now at this point, we check its right pointer. Guess what? It's the null pointer. So we're now out of the while statement. That conditional has evaluated to false. And we're going to return the address of the node whose key value is 22. And guess what? Within this tree, the key value of 22 is the maximum value found within our binary search tree. And again, this is all we can easily calculate. If you look at this, we don't even have to look at the key value stored in these nodes. Why? Because by this property up here, it is guaranteed that as we continue stepping right into the right subtree, the key value is going to be at least as big as the previous node. So if we keep going through, we're guaranteed when we've gone as far right as we can, that node based on the property has to be the node that has the largest key value. Likewise, if you're looking for that of the smallest value, you don't have to look at the key values. You just keep stepping left until you can step left no more. And by the binary search tree property, we're guaranteed, without even looking at the keys, that we're at the node with the smallest or minimum key value. So notice that just by these properties, we can run through and we can find the minimum maximum value without ever looking at the key value stored within those nodes during the traversal. Pretty neat, eh? So with that in mind, let's go ahead and get into searching. So we've talked about how we can find the node with the minimum key value, the maximum key value. What if we want to find a node storing a specific key value? That's next. Stay tuned.